Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 26, 2025, just 2 days ago. It tackles the core problem of using a large language model as a judge by showing how the raw fraction of answers it labels as correct can be systematically biased, and it offers a simple way to both debias that score and attach statistically valid confidence intervals. The paper is titled, How to Correctly Report LLM-as-a-Judge Evaluations, and as we will see later, the implications for trustworthy model evaluation are quite significant. Alright, Figure 1 lays out how judgment errors arise when a large language model evaluates answers. The left circles show the ground truth, correct or incorrect, while the right circles show what the model judges. The arrows labeled Q1 and Q0 represent correct decisions, and the arrows labeled 1 minus Q1 and 1 minus Q0 represent mistakes. This diagram makes clear that both kinds of error systematically distort the raw fraction judged correct. Well, Figure 2 shows how that error pattern actually bends reported scores and how the adjustment fixes it. The left plot shows the naive expected accuracy, which starts too high when true accuracy is low and dips too low when true accuracy is high. The center cartoon illustrates using a calibration dataset to estimate Q0 and Q1, then feeding those into code that outputs a corrected estimate and confidence interval. The right plot shows the bias-adjusted accuracy lying on the diagonal, with a narrow gray band representing a 95% confidence interval around the true line. Alright, Figure 3 turns to how much calibration data is needed for tight confidence intervals. The plot shows interval length on the vertical axis shrinking as the total calibration set grows along the horizontal axis. Each color corresponds to a different reported accuracy level, from 0.3 up to 0.9. Solid lines, using the adaptive allocation rule, consistently give shorter intervals than the dashed symmetric allocation lines, so they reach any desired precision with fewer human labels. So, Figure 4 backs up those ideas with simulation evidence. The left panel shows that the naive p-hat curve bends away from the diagonal, while the bias-adjusted theta-hat tracks the true accuracy closely and keeps its confidence band tight. The middle panel reports coverage, where intervals from theta-hat stay near the desired 95%, while those from p-hat nearly collapse. The right panel compares equal versus adaptive calibration splits and shows that the adaptive rule consistently yields shorter confidence intervals across accuracies. Alright, Figure 5 turns the statistical recipe into concrete Python code. The point estimator function applies the Rogin-Gladden style formula, taking the naive accuracy p and judge reliability Q0 and Q1, then clipping the adjusted accuracy to stay between 0 and 1. The confidence interval function then performs the add two corrections, computes the standard error from both test and calibration data, and returns a lower and upper bound. This snippet makes the whole procedure directly usable for anyone running large language model as a judge evaluations. So the big message is that large language model as a judge scores should never be taken at face value, because judgment errors systematically bias reported accuracies. Using a small human calibration set, the bias-corrected estimator and confidence interval recipe make evaluations far more trustworthy and data efficient. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.